Let me enable conversation view so you can ask questions on that, and let me share my screen. So I hope you are able to see my screen also properly. Right?
Yes, sir.
Okay. So what did we do last time? We dealt with something called regular expressions, which are kind of patterns to specify, a sequence of occurrences of symbols. And if you take different words, some of the words may match those patterns, some of those words may not match those patterns. And here is an example of a pattern that we saw. I'm just repeating what was done last time. Uh, uh, so what does this pattern say? It says either we have a 1 1 or a 0, and this pattern is repeated arbitrarily many times, star 0 or more times. So you got 1 1 followed by again a 1 1 followed by 0 followed by 1 1 followed by 0 followed by 0, etc. And this occurs some number of times. This is followed by a behavior where two zeros occur in sequence or a 1 occurs, and this pattern is repeated some number of times, right? So that is what a regular expression is. Star is the Kleene closure, which says repeat the pattern to which it is applied 0 or more times. And you can see from this that this can be converted into its equivalent automaton. We guess this as follows. In the start state, either you have got the pattern 1 1. So let me draw it here. The pattern 1 1, or you have the pattern 0, and this is repeated arbitrarily many times. At some point you decide to exit with this part of the pattern and go to this part of the pattern. So you make an epsilon transition, and there either a single one can occur or two zeros can occur, right? So in the second part, the number of zeros you will get will be even, and zeros will always occur in pairs. So this is what happens. So this was the sort of intuitive conversion of regular expression into patterns. What are regular expressions? Regular expressions are constructed by giving what is called its grammar or its abstract syntax. That is, every letter of the alphabet constitutes a regular expression. The symbol phi constitutes regular expression. Symbol epsilon constitutes regular expression. You can make bigger regular expressions out of smaller regular expressions alpha and beta by using either catenation or plus, which denotes union, or the Kleene closure operator, right? And we made use of these operators here. See, the dot is implicit. When I say 1 1, what I actually mean is 1 dot 1. Huh? Okay. So that is what was happening, and we can write regular expressions like this. Now there was this question, what kind of languages are represented by regular expressions, and we had this theorem which said that for every regularization alpha we can construct a normalized epsilon NFA of alpha such that language of alpha is same as language of the automaton of alpha, right? And we did this construction by structural induction, meaning what? Every alpha, every regular expression is either an atomic regular expression or it is constructed out of sub expressions using one of the operators dot, plus, or star. This is the only way in which you can get more complex expressions out of simpler expressions. So if we know how to construct automata for simpler expressions, we can compose this automata to get the automaton for the larger expressions. Such definitions are called definitions by structural induction on alpha, right? So for if we have atomic expressions like a, epsilon, or phi, their corresponding automata are given here. For a, it is this. For psi, it is here. For epsilon, it is this, and for phi, it is this. So I hope there was no confusion with this. I'm just repeating what was done last time. And if you have more complex operations such as alpha plus beta, you can inductively assume that you already know how to construct the automaton for alpha. You already know how to construct the automaton for beta, and now you will construct the automaton for alpha plus beta. So you know A alpha and you know A beta. How do you construct A alpha plus beta is given in this diagram, where this is of course A alpha and this is A beta, right? This just takes the union of those two automata, and that is what plus denotes. So this is what we do. So you saw all these constructions before. This was for catenation and this was for Kleene closure, right? So using these rules, we can convert any regular expression into its equivalent epsilon NFA. Okay. And then there was this question of the size of the constructed automaton, and there were some questions here. So how do we measure the size of an automaton? Can anybody tell me what is the size of an automaton?
The total number of states in the automaton.
Right. The number of edges or the symbols on the edges don't matter. We count it basically by giving the number of states within the automaton. That is the size of Q part of the automaton, right? How is the size of a regular expression counted? You count the number of symbols occurring in that. That is all the atomic patterns and all the dots and pluses and etc. So here this was a mistake, right? This should have been 10. What is the size of this regular expression, which is a plus b whole star catenated with a dot a dot a. So how many symbols has it got? It has got a, b, a, so 5 letters, you know. Then one plus symbol, one star symbol, that is 7. And then how many catenations? 1, 2, 3 and 3 catenations, right? 3 dots between those parts totally. So I will get totally 10. So this is how the size of a basically you just count number of symbols within the regular expression ignoring brackets. Okay, and between two, when you write a, you assume that there is a dot in between, of course. Right, this is the size of the automaton. And then we had this theorem claim that the size of the constructed automaton using our method is of the order of big O of size of alpha. What do we mean by this? How will we show this? So I'm going to do the proof little more carefully today so that you can understand. We prove this again by structural induction on alpha. And what we prove is the following, that the size of the constructed automaton for any regular expression alpha is less than equal to twice the size of the regular expression. Remember, the size of the automaton is number of states of the automaton constructed. Size of regular expression is the number of symbols occurring in the regular expression, right? And we will show this. And we will again show this by induction on the structure of the regular expression. That is, we will show this for all the atomic regular expressions. And then, assuming that this property holds for components, when a larger expression is made out of them using operator dot or plus or star, we will show that this property is preserved. So we will do this proof now. But what we are trying to prove is clear. So this big O just says that, you know, F is equal to big O of G. What does this mean? This means F is equal to C1 star G plus C2 for some suitable constant C1 and C2. This is what it says. For whatever arguments that F and G take. I mean, they take the same argument, right? So you have to exhibit some constants. In our case, we will choose C1 to be 2 and C2 to be 0, right? So you learn about this big O notation in your algorithms class. But basically, you know, in our case, we will prove this property, that for any alpha, the size of the automaton for alpha is less than equal to twice the size of the regular expression. This is what we will prove. Okay. And how will we prove this? We'll prove this by induction on the structure of alpha. So what is the first thing we have to prove? We have to prove the base step, which says if alpha is either a letter or phi or epsilon, we have to check that the size of its automaton is less than 2. Why? Because size of alpha in that case is 1. You are using only one symbol. You are using either symbol A or symbol phi or symbol epsilon. That contributes size 1. So 2 times that is 2. And so we have to show that the automata for these 3 atomic regular expressions is at most 2 states. And let's look at what we have done. For atomic regular expressions, we have constructed these 3 automata and each have no more than 2 states. Right? So I hope you are clear why this base step holds. That is, if alpha is of the form either A or phi or epsilon, then the size of its automaton is at most 2. That is, it has no more than 2 states. That is what we have shown. And that discharges this requirement for atomic regular expressions. Questions?
Sir, can it be 0?
Which one?
The A of alpha, the size of A of alpha.
Well, we can't have an automaton with 0 states, right? We'll construct some automatons. It will at least have 1 state, right?
Okay.
Yeah. But it can be 1. It need not be 2. It
Theoretically
has to be less
speaking.
than. Yeah.
Theoretically speaking, it can be 0, right?
How? Oh,
Means if there are
if
there
you
are no
reduce it,
states.
if you reduce it and there are no
Yeah.
reachable states. Yeah,
Yes.
but that doesn't matter, no? Then also it's okay.
Yeah.
The theorem holds. I mean, typically
Yeah,
we
theorem.
will not remove the start state.
Hmm.
Okay. Yeah. Now, what is the induction state? Can anybody tell me what should we prove? So let's try to prove it for the patterns of the form alpha plus beta. What should we do? Assuming that automaton for alpha, that is A alpha, size of A alpha is less than equal to 2 times size of alpha. You assume this. Similarly, you assume that for beta, and then you prove that the automaton for alpha plus beta is 2 times the size of pattern alpha plus beta. Okay. So what do we do? So let alpha be of the form beta plus gamma. Okay. So we are assuming that our pattern alpha is now made out of some sub patterns beta and gamma using the plus operator. And we already, so what is the size of alpha? What is the size of this expression?
Yeah, 2 plus size of beta and plus size of gamma.
No. So the automaton for alpha,
Type.
which is given here. Where is automaton for alpha? Sorry, not this slide. This is the automaton for beta plus gamma, right? This is beta and this is gamma, right? How many states it has got? The number of states in the A alpha, A beta, and the number of states in A gamma plus 2 extra states, right? You see, the number of states in this automaton is all the states of the first automaton, all the states of second automaton plus 2 extra states, right? So you can see that the size of the automaton for alpha, which is alpha is equal to beta plus gamma, is equal to 2 extra states plus the number of states in the automaton for beta plus the number of states in automaton for gamma, right? So this is by the construction of the union automaton. Is the first line clear to you? If this is not, you are already, lost. So this is the time to...
Sir, isn't it 1 plus A of beta plus A of gamma?
See how many states are we adding when we take union? One new state S2 and one new state F2. And then we are retaining all the states of the first and the second. So we are adding 2 extra states.
Yes, sir. Okay.
Yeah. If we had a clever construction which added only 1 state, then I would have put 1 there. Okay. Here I'm putting 2 because we added 2 extra states and we retained all the states of the old automata, right? Now, by induction hypothesis, we can assume that for the simpler expression in size called beta, we know that the size of A beta is at most 2 times the size of beta by induction hypothesis. Right? So by induction hypothesis, we can replace this term by this term. The red underlined term can be replaced by the red underlined term. Why? Induction hypothesis. This is a very important step. See, induction is our friend. We can assume something about beta and then show that. Similarly, for gamma, the size of automaton for gamma, we can assume is at most 2 times the size of gamma. Right? By induction hypothesis. For simpler patterns beta and gamma, we assume that this holds. And then we are trying to prove this for the larger one. Just as, when you are trying to prove property of all natural numbers, you assume for it for property to hold for n and you prove it for n plus 1. Here we are doing something similar. So is this step clear? This is the main step of this proof, induction hypothesis, induction step, right? And we get less than equal to. Now, what is the size of this pattern alpha? It is equal to the size of beta plus size of gamma, right? Size of alpha by construction is equal to size of beta plus size of gamma plus 1, right? Because we have written it as beta plus gamma. We have so we are using as many symbols as in beta, as many symbols as in gamma, and one more symbol plus. So it is size of beta, size of gamma plus 1. This is size of alpha, right? And if you take 2 common, what you will get is 2 times the size of alpha. So what you have proved is size of the automaton for A alpha is less than equal to 2 times the size of alpha. It's a very simple derivation, but I think it is the proof method which is important. We prove it by induction on the structure of the regular expression. And so we have shown this for the operator plus. We need to. Is this clear to you, this induction step for plus operator? Any questions there? I think class is very, very silent. By the way, today's is the last topic which will be covered in the midterm. We'll have one more class on Friday, which will be a kind of tutorial. You know, I'll release some questions today for you to try. And then on in the Friday class, we will see solutions to some of these. And the exam will be, you know, if you do these questions, prepare these questions well, at least you can do reasonable part of the exam well. Of course, everything that has been taught will be covered in the exam, but the questions will launch you well on the way to that exam. So it is in your interest to solve the questions which I'll release today, okay? And then come for the tutorial in the next class. So I hope this induction step is clear to you. If there are no questions, I will go ahead. It's not a difficult proof, but the proof method is what you should learn. That to prove some property of some function you have defined on regular expression, like its automaton construction, you prove it by first proving it for the atomic expressions, and then you prove it for each way of constructing bigger expression out of smaller expression. This is called proof by structural induction. And our principle of natural, induction on natural numbers is an example of structural induction. Okay, you proved it for plus, but you have to prove it also for beta dot gamma and beta star. And I will leave this as an exercise for you to do. Okay, so you should try to solve this. Just as I've done it for plus, alpha equal to beta plus gamma, you should do it for alpha equal to beta dot gamma and alpha equal to beta star. So please complete this proof. That's your job. Okay, you may even be asked to do this. So that finishes the size of the automaton. Okay, and what have we proved? Basically, we have proved that for every regular expression alpha, we can construct an epsilon NFA and hence also a DFA such that the language of alpha is equal to the language of the automaton constructed. That is, they both denote the same language. And the size of the automaton constructed is linear in the size of the regular epsilon NFA, which doesn't blow up, which means the size of the DFA is at most exponential. It is not, right? Right. So we know what is going on in the worst case. Somebody asked last time about the converse. That is, we know that every language which is denoted by a regular expression is recognized by some finite automaton. What about the converse? And here we prove the converse. For every non-deterministic finite automaton A, we can construct a language equivalent regular expression reg A. That is, for given A, we can construct a regular expression called reg A such that language of A is equal to language of reg A, right? That is what I mean by language equivalent, right? This is the reverse construction. That is, let me go. Given an automaton like this, we want to come up with some regular expression like this. Now in this case it was easy to guess. We saw that there was this forward movement with epsilon. So first we write down regular expression for this subpart, and then we write down regular expression for this subpart, and then we can do this. But that kind of trick doesn't work always. Okay, and we need a general method, and the general method requires a little bit of work. So we are going to do this method. Now this theorem, both these theorems were originally proved by a logician called Kleene. Okay, but there's a slightly better method which proves this theorem, and this goes also by the name of, fancy name, McNaughton Yamada lemma. So, if you want to impress somebody about your knowledge of theory of computation, this theorem is called the McNaughton Yamada lemma, and it's part of the Kleene theorem with a superior proof due to McNaughton and Yamada. Okay, doesn't matter. The names are not important, just for your knowledge, general knowledge. So this theorem is what we want to prove. Now please concentrate. Okay, so how, given this automaton NFA A, we are going to construct its regular expression, right? So given this A, what do? We define a regular expression called alpha, which takes three parameters: a state P, a state Q, and a set of states X, where X is an arbitrary subset of Q. So for every such X, every such P, and every such Q, we will define such a regular expression, right? And if we can define this expression for smaller x's, then we can construct the expression for larger x's. So again, we will compose smaller, terms like this into bigger terms. That is the method, right? But first we have to understand what such a regular expression denotes. What is its meaning? What is our intention? Our intention in defining this alpha with parameters capital X, P, and Q is the following. So here P and Q are some states, and X is some set of states. Let me give you an example right away. Here I have this automaton, right? This happens to be DFA, but it could be NFA, and I'm defining alpha of P, the start state, Q, the target state, and this X as the set PQ. Here there are curly brackets, but I will omit curly brackets for convenience, right? So in this case, X is X equal to the set PQ. My start one is P and the last one is R, right? So I will define, and the corresponding regular expression will be something like this. So we'll see how to calculate this. Okay. And what does this denote? Alpha of PQX. It denotes the set of all words such that the automaton has a run on that word W, starting from P, ending up in Q. So you start with P. So in alpha, P, Q, and X, you start with P, you end with Q, and all the in-between states, not counting the start state and the end state, are in this set X. So all intermediate states come from X. Your start state is of the run is PQ. It need not be the start state of the automaton. And the end state is Q. So let me give an example. I think this is best done by an example, best illustrated by an example. So what I will do is, so let me calculate alpha of QR and empty set. So I'll denote this by phi. So you cannot have any empty state. So what can I have? I can have a run which starts in Q. It does something and it ends up in R. I cannot have any intermediate state because the set of intermediate states is phi. So the only such run going from Q to R is 0, right? So this pattern will be just a single letter 0. Do you see how alpha QR with X equal to empty set will be 0? Because the only runs which start with Q end up in R and pass through no intermediate state is going directly from Q to R without having any intermediate state. So this is equal to 0. right? What happens if I change this to, so I will change this, and now I will allow you to go through intermediate state Q also. What will happen? I can go from Q, I can go to Q because that's an allowed intermediate state, but there's no transition going from Q to Q, right? So it will not change. Let's take the example of Q comma R. That is, you are allowed to stay in states Q or R in between. So from Q, you can go to R. From R, you can come back to Q, and then you can again go to R. And then from Q to go to R, you will use a 0. Here you will use a 1. Here you will use a 0, right? So basically, you can take this loop any number of times because you are allowed to return to Q, because Q is one of the intermediate states and R is also an intermediate state. So you can pass through Q and R any number of times. So the pattern you will get in this case will be what? Can anybody guess?
Cleaning closure of 0, 1 concatenated.
Yeah, so you call it 0, 1 star, right?
Concatenated with 0.
Concatenated with 0. Absolutely. Absolutely. Right? Because finally you must always, so you do some number of these repetitions and finally move from Q to R. So 0, 1 star 0. So I think you are getting some intuition about what is alpha x PQ, right? Any questions? So we'll see one more example here. You know, what is alpha of PR passing through Q? So you want to go from P to R, but you are allowed to visit Q any number of times in between. What can you do? If you want to go to P to R, the only path is this, and then this, and then you can come back, or you can come back to P. But you are not allowed to come back to P because P is not included as an intermediate state. You can come back to Q, right? You can come back to Q, but for that you will have to first reach R, and R is not an intermediate state. So you cannot take this loop also, because although you can use Q as an intermediate state, you cannot use R as an intermediate state. So once you reach R, you have to finish. You cannot go exit, right? So the only path which allows you to go from P to R, visiting Q arbitrary number of times, is 1.0. Do you see that? So the regular expression PR with set of intermediate states Q is 1.0. And we are doing this by our intuitive understanding of what this automaton does, right? So I hope this is clear to you. You're going to get lots of exercises about converting NFAs into the regular expression. So you better understand this well. You can ask in chat also. What is alpha P going from P to R, where you can visit both P and Q arbitrary number of times, but you cannot revisit R. You have to end in R, and that is going to be the first visit of R. So you can go pass via P any number of times, you can pass via Q any number of times, but you have to end in R, and that is the first occurrence of R. So the only path, you cannot do this QR loop any number of times because you will have to visit R several times. That is not allowed, right? So what you can do is you can go via this loop any number of times because P can be visited any number of times. So you get 0 star, and then you must take this path. So you get 0 star dot 1 dot 0, right? So I think if you have understood these examples well, then things are easy. Who has a problem with this? So can somebody calculate for me this exercise? Alpha of RP with intermediate states QR. What will this be? So you have to start with R, you have to end up with P, and in between you can visit Oh, sorry, I'm making a mistake. I wanted PQ. You can visit P any number of times and Q also any number of times. Let us remove Q also. Let's simplify life. Just have this. Sorry, new question. Yes. Alpha RP, where you want to move from R to P, but P can occur any number of times. What will it be?
So 0.0
0
star.
0.0 star. Why? Yes, because you can start with R, you can go to P, but this P can be intermediate and you can repeat this and at the end you will be in P, right? You cannot go to Q at any time, either from R or from P, right?
Yes,
so
sir.
this very good. So I think you're getting a little bit of what this entity P, Q, X denotes, right? Of course, we have constructed it by intuition on a given automaton. There must be a systematic way to compute it. But if we want to denote the language of this automaton, okay, my claim is that this language is same as alpha PP. You must start in the initial state P. You must end in the final state P, right? And you can pass through any of the states any number of times. So you have you take your X to be set of all states PQR. So this will include all runs which start in P and end in P, right? So if we can compute this regular expression, it will denote the language of this automaton. Do you agree with that? Because what is the language of this automaton? It starts with the start state, ends in the final state, and visits some states in any of the available states as an intermediate state. So I'm allowing every state to be visited as an intermediate state, including P, including Q and R, right? So this denotes the language of the automaton, right? Any confusion there? So the regular expression for the whole thing is, now, of course, in this NFA, we had only one start state and one end state. But what if you have several start states and several end states? You choose one start state, P, choose one final state, F. So you choose one start state, P in I. Look at just this expression. Forget the rest of the slide. Choose some start state, P, some final state, F, and calculate alpha with all states as intermediate states, starting from P going to Q. So this will represent all the runs which will take you from initial state P to the final state Q. And they'll represent all the words which will be accepted by starting at P and ending at Q. And you do this for all possible pairs of initial states and final states and do plus of those regular expressions. You will get the regular expression for the language of the automaton. So if you can...
Sir, the question that you showed just before this in the previous slide, how will you write it? Like, yeah, that question, how will you write it down? Like 0 star 100 whole star.
Which one? Oh, the
alpha
of R2P going through P. This one, right?
No, sir, this one, the bottom one, PQR P2P.
Right. So you don't know how to write it here. We will calculate it. No, I'll show you the method to calculate this, how to write this. That is, you are right. I mean, it's not very straightforward, right? You cannot guess it just by looking at the diagram. Which is why this lemma is a little tricky. Okay. But for simple cases, you can write it, right? Yes. For example, the above two cases are easy. But there are cases where it becomes difficult, and when this automaton has got, let's say 20 states with all kinds of loops, things get very difficult. So you need an algorithm, right?
Yes, sir.
So that's what we are going to see. Yes,
I
please.
have a doubt.
Yes.
In this last one, the alpha P2P PQR. So the states PQR should occur.
No, they're not. They should occur. They can occur.
They can occur. Okay.
Yes.
It's not that they should occur.
No, they don't have to occur. That would be a very different thing. So all the intermediate states are from X.
Okay.
What it basically restricts what states should not occur as intermediate states. That's all it does. It's a negative construct, not a positive constraint. Okay. So that's a good question. Sir. Yeah, very good. Okay. So what I'm saying is, suppose you can construct such alpha PQ for any set X, then my claim is that for any arbitrary automaton, it's the regular expression for that automaton will be given like this. Choose a pair of an initial state and a final state and calculate alpha Q PQR, capital Q denoting set of all states, right? So this will denote all those words which are accepted by the automaton starting from Q and ending in small q. Right, starting from P and ending in small q, right? And you take all possible pairs where small p belongs to the initial state and small q belongs to big F. You calculate alpha PQR and do plus of those, you know, then you will get the regular expression for the whole automaton. Agreed? Because what is the word, which words will be accepted with the automaton? Those words from which there is, you can start in some initial state, you can end in some final state, and there's a run. And that run must pass through some sequence of states. But Q allows every possible intermediate state. So all possible runs will be included, accepting runs will be included. So it is easy to say that this is equal to the language of automaton, right? So if you can calculate this entity, then you can calculate this larger entity. I hope this much is clear to you. I have not done this part. I have not done this part yet. Just the last line. So I'm just motivating why calculating this PQR is important. Okay. So now how do we calculate this alpha? Something like this. That is the question, right? And that was the question that was asked by somebody. Okay. So how do we calculate alpha for any arbitrary P, arbitrary R, and an arbitrary X? How can we calculate it? We can calculate it recursively. And the recursively we calculate it like this. Alpha PR with no intermediate states where P and R are distinct. P is not same as R. Okay. If P is not equal to R, since you are not allowed to go through any intermediate states, you must directly go from P on a letter AI to R, right? So basically, let AI be a letter such that from P on AI you can, oh, this should be delta because we have non-deterministic automaton, where R belongs to delta of PAI, which means what? From P on letter AI there is an R. Collect all such letters and add plus with between them. And you get the regular expression telling you how you can move from P to R without going through any intermediate state. No rocket science there, right? Agreed? So suppose I have an automaton like this. And I can go here on an A, I can go here on a B, and on a C I go here, right? Right? And this is my P and this is my R. Then what is going to be my alpha PR on empty set? Anybody can tell me? This is P. This, sorry, I already wrote that. So I can go on an A, I can go on a B. What will be alpha PR? How can, with empty set of intermediate states? Come on, this is
A
easy.
plus B.
Why? Because delta of P on A will include R, right? Maybe I can put an A here also. Still, so what is my delta of P on A? It is equal to, this is Q. It is Q comma R, right? And since R is included in it, I will include A in this. Similarly, I will include B in this and I'll get the expression A plus B. So that is this rule. So is the rule clear to you? I hope the rule is clear to you. So I'm going to rub all this and I'm going to give you one more example. By the way, wherever I have written small delta, it should be capital delta because we are dealing with non-deterministic automaton. Okay. What happens when P is equal to R? Can anybody guess? So what will be alpha of PP without going through any intermediate states? So suppose I have got here A, I got here B, and then on an A, and this is my P, this is my Q. And on an A, I can also go from P to Q. On an A, I can go from P to P. On a B, I can go from P to P. In that case, what will be, can anybody tell me what will be alpha of PP without going through any intermediate state?
Empty word.
Epsilon. But also on an A, you can go from P to P without going through any intermediate state. P is allowed to be the start state and the end state, but there should be no intermediate state. So it will also include A, no?
Yes,
Our run
A and B.
PAP, right? With no intermediate states. Right. So A and B, right? So in previous case, we had just the letters going. When P is same as true, you add an extra epsilon. You can see that, right? That's what you are doing. So this is the rule. Alpha PP with no intermediate states is A1 to AK, where A1 to AK take you directly from P to P itself. There is a self loop from P to P on each of these letters A1 to AK plus epsilon. Right? So you can calculate when given an empty set of intermediate states, you can calculate this for any pair PQ, right? By these two rules. That is the basic. This is the base case of the recursion. Any questions here? You will have to do this construction, in your homework. Okay, finally, suppose we have X which is non-empty, right? X is an arbitrary set of states which is non-empty. We want to calculate alpha PR on set of intermediate states capital X. The claim is that if we know how to calculate it for this smaller case, that is set X minus Q. X minus Q is a smaller sized set than X. We have removed one state from it because we are taking Q to be some state in X. So we pick an arbitrary state in X and we remove it. We get a smaller state. So we'll call this as let's say Y, right? Suppose we know how to calculate P alpha, some arbitrary, QW on Y. Suppose we know how to calculate all such triples this, where Y is a smaller set. Then my claim is you can calculate it for PR using this formula. Okay, so let us look at this reduction. What is this entity denoting? The entity on left hand side, it's denoting in the automaton you start with P, you go through some intermediate states. Let me write down here as Q1, Q2, right? And finally you wind up Q3, Q4, and then finally you wind up with R, right? And whatever is the sequence of letters we take you like this, where Q1, Q3, Q1 to Q4 belong to this capital X, right? All such runs, not necessarily of length 4, but longer also, will be in this, will contribute this alpha PR X, right? Now there can be two kinds of runs, we have got this distinguished state Q of X that we have decided to remove from X to get Y, right? Okay, so there will be those runs which will go from P to R without ever visiting this small q, right? And they will be given by this, that is alpha PR, going through set of intermediate states. We do not include this small q, right? That is one kind of things which will take you from P to R. Agreed? So this is the simple case where you're completely avoiding this set q that you have chosen from X. So all the paths which avoid that q is one. The second case is that you go via that q. So, from P, I'll draw a double arrow saying through many mu's, you will hit q for the first time. Okay. Then what will happen? You will again hit q for the second time. You will hit q for the third time. and then maybe this was the last time that you visited Q, and then you went to R. So, you know, this execution I can break into 3 parts. From P, I hit Q for the first time, then I repeat Q several times, you know, and then from Q, I move to the R without ever visiting Q again. So I move from P to Q without visiting Q as an intermediate state. That is, I have got P to Q without having Q as an intermediate state. Then I go from Q to Q without visiting Q as an intermediate state, and this thing I repeat several times by putting this star. And then I have this. So if I underline this and call this as A, call this part as B, call this part as C, then what I have is any execution will be of the form A followed by B, B, B repeated some number of times, and then a C. Right? Where B may repeat even 0 times. 0 or more times, because you can go from Q to Q several times. But in going from Q to Q, you should not visit Q as an intermediate step. This is what I'm saying. So you can see that all the runs which go from P to Q, P to R via Q can be broken up into this structure. They will have, you know, a part A where you go from P to Q for the first time, then Q will repeat once more without having any Q in between. Then Q may repeat once more without having Q in between. And then from the last Q, you will go to R without having any Q in between. So you can recursively write it as this second thing after this plus. So I think this is the only thing that you need to understand. There's a lot of notation, but the idea is very simple. You know, the first red underlined thing here, you know, let me underline it. This double underlined red is the case where you go from P to R without ever visiting small q. That's the direct going from P to R, going through all other states of X possibly, but not visiting Q, small q. Okay, that is one case. Those are one kind of executions which will take you from P to R. The other kind of executions are of the form which is drawn in this line, which says from P you visit Q for the first time. That is given by this first underlined blue called A, right? Then you visit Q to Q, right, without ever passing through Q in between. And that is given by this B. And this B can be repeated any number of times because then you are visiting Q several times, right? So that you do by giving a star. And finally, from the last time you visited Q, you go to R without visiting Q in between. That is given by this expression. So after this plus, this second term gives you all the ways of going from P to R via Q. So this complicated looking expression, which is actually a simple expression, actually defines alpha P R X. So is this clear or sort of not so clear? We'll be working out an example, but you must remember this recursion. That is, calculation of alpha PR with a set of states X is done by picking some state, arbitrary state Q from X, and then reducing it to simpler calculations. And why are these calculations simpler? Because the set of intermediate state becomes smaller. And finally, it will become smaller and smaller recursively till you get empty set of intermediate states, which you can solve using the first two doubts. This is how the calculation is done. And this is the McNaughton-Yamada method. So questions? Questions, confusion, if you want me to repeat something, please ask. Is it too much?
Sir, could you do an example?
Yes, I'm doing example next, but just stare at this equation a little bit. We wanted to calculate this alpha PR on X, and in calculating this, we are using alpha arbitrary state, you know, starting state such as QQ or PQ or something, which is different from this PR, but with smaller set than this X, right? We are removing something from this X and calculating recursively in terms of it. Okay, so I'll do an example. So just we'll come back to this this slide again. And then I said it, once you can calculate this, the language of the automaton is given by this regular expression. You calculate it for every initial state P, every final state Q. You calculate this expression and take pluses of those. So we'll do an example. Okay, in this case, there is only one start state and one final state. This was the same example as before, right? What will be the language of this automaton? It is given by this expression. Do you agree? First, you have to agree that the language of this automaton is given by this expression, which we will have to calculate. Who doesn't see this is the regular expression for this automaton? Everybody. Suppose I had this also as the start state. Then what would be the regular expression for this modified automaton? Can somebody tell me? It will be alpha
Q2
with, I'll write capital Q as set of all its states. Okay.
Okay.
And the second one will plus alpha. So one possibility, you start
QP.
in P and except with P. You start with
QP.
QP and then set of all states, right? If I had additionally R as an accepting state, then I will have also alpha PR with Q. So I will add more pluses here and plus alpha QR of capital Q, right? So for every pair of start state and end state, I'll calculate the corresponding expression, right? This is easy, but let's go back to our original example. So you can see this in video. Huh? Yeah, this will have to go because I need to go back to this. So the language of this automaton is given by this term. Here we have only one pair of start and final states, right? This. Now, how can this alpha PP with set of intermediate states PQR be given? I choose to remove from this the state Q. So from this set of states PQR, I choose to remove this small q and do recursively calculation using the remaining set PR. So what do I do? By this equation, my X is the set PQR and I remove small q from that. So I have to calculate alpha PR on X minus Q. That is, I calculate alpha PP on the set of intermediate state PR. So from PQR I have removed Q. So everywhere I'll get set of states as PR only, right? But I'll have those runs which will take me from P to P without ever visiting Q, or those runs given in this bracket which will visit Q. So runs which go from P to P without visiting Q and runs from P to P which will visit Q. And the runs which go from P to P visiting Q will be those runs which start from P and end up in Q for the first time. That is given by this underlined part, followed by runs which go from Q to Q, right? And that I repeat several times, because I can go from Q to loop from Q to Q several times, right? And then I go from Q to P. So is this line clear to you? Because then we are going to calculate all of these subterms. And this line is obtained by applying this equation. Okay, what we will do is we'll do one more example instead of this. Okay, so let's try to write down alpha P R Q. Can somebody tell me how to write, PQR, removing Q. How do we write it? So we factor the right hand side by choosing small q to remove. What will I write here? What will be the first term by this equation? So this is the term that we are trying to instantiate there. What will I get? I'll get alpha P comma R going through what intermediate states? I've chosen not to go through Q. So it will be PR. You can choose any of these three states, huh? But I've chosen Q. And then I'll get this bracketed term, like the bracketed term here. First part will be alpha PQ going through PR, followed by alpha Q going through this PR, and that I can repeat any number of times, followed by, let me remove this, alpha QR going through PR. So is this clear to you? Why we got this? It is just an instantiation of this equation in this example. So unless you can expand this, you can't apply this method. So I gave you one example here where I had PP, here I have got PR. I think you will have to do examples of this yourself. Now, we know that this regular expression is same as this irregular expression, because we have expanded this to this. Now each subterm of this will solve. Now what is alpha PP with PR? What is this term? I calculated here. So alpha PP with set of intermediate states P and R. I can't go via Q, so there's no point taking any this loop. I am allowed to take this loop. So alpha PP with PR is 0 star. I'm not applying the rule there. I'm directly getting it. Actually, we should apply the rule and get this. But I'm just guessing this. So alpha PP going via set of intermediate state PR will directly give me 0 star. Why? I have not applied this rule. I have directly guessed it. But this one I have not guessed. I have applied this. So this term here is calculated by this. Similarly, alpha PQ with PR, which I require here, this red underlined thing. So let me remove all the underlines and then show you what I am calculating. Okay, so I have got all of this. First, this is what I calculate, and that is done by this thing here. Alpha PR, alpha P2P on set of intermediate state P and R is given by 0 star. And this I have done an ad hoc calculation. I should actually calculate it using this equation, but it becomes cumbersome. So for this example, I have calculated here. We can expand that later in the next slide. But this is what it will be. Similarly, what will be, I also need to now, next I need to calculate this term. So I calculate it here. What is alpha PQ going via PR? You can repeat, go from P to Q, but you can repeat R any number of times, but you can't have Q occurring intermediately. So this loop is forbidden because you cannot exit from Q, because then Q will become an intermediate state. So the only loop allowed is this, and you have to go from P to Q. So basically the only path you can take is go from P to P and then go to Q. So you will get 0 star 1. Again, this is an ad hoc calculation. I should ideally do it using expansion like this, and we will do one example of that in the next slide. But this is what I have calculated. For simple expressions, you can do this ad hoc calculation. And for the more complicated ones, you can do it like this. Okay, so this term also we have done PQ this thing here. Next, we have this term alpha QQ with set of intermediate state PR. So what will be alpha QQ? You start with Q, end with Q, but you can visit PR in between. What will you get? Alpha QQ going from, and my claim is you will get this expression. Okay, so we'll do this formally. This case we'll do formally. Okay, and then finally I have to calculate this, which is calculated here. So all these subterms are calculated. So, and that gives us, since this first term is given by this red underlined thing, the second term is given by this. Okay, I'm underlining them in blue. we can put it all together and get this regular expression as the regular expression for this automaton. So it's quite a complex regular expression. Is the method clear to you? You will have to get some practice of doing this calculation, but the method should be clear to you.
Sure.
Yes.
It was your choice to remove the state Q, right? I mean, we
Right.
can get some different expression by removing different states.
Right. So yes. So question is which state to choose to remove, right? The method
Yes, sir.
guarantees that no matter what state you choose, you will get something smaller, right, in the capital X. And then recursively from that smaller X, you will remove further one more state to, so you can always end and get a regular expression. But the complicated complexity of the expression you get depends very much on the state that you choose. Okay. So heuristically, it is better to remove some states rather than others. Okay. But every choice will lead you to some regular expression, and they will all denote, there will be different regular expressions you get. They will all denote the language of the automaton. So first of all, that is clear to you. There is some choice here in which state to remove. Depending on which state you remove, you will get different regular expressions. But they will all denote, the language of the automaton. So there are many different regular expressions which denote the language of the automaton, and each method of removing the state will give you a regular expression. It is recommended that you remove a state with maximum number of incoming and outgoing edges. So, because my Q had, lot of edges coming in and out of it, I chose to remove Q. So, you basically look at the in degree plus out degree of the node and then choose. But this is just a heuristic. Okay. So in examples, it is advantageous to choose those nodes such that a lot of paths go via it, right? You get rid of that first. Okay. But
Sir, also
theoretic,
one more doubt.
Yeah.
Like here, the automaton that we're given, it has only 3 states, right? So
Yes.
yes. Theoretically, we can even have a regular expression with just 2 symbols. I mean, that will also satisfy the bound that we have. So how do we like intuitively see which automaton will give rise to a very large regular expression like here?
Very difficult to
This is
predict.
very far away from the bound, right?
Very difficult to predict. So I think the correlation between the complexity of the regular expression and the complexity of the automaton is not very direct. It also depends on the kind of graph there is. Okay. And I think it is quite out of scope of this this course to discuss factors which affect the complexity of the regular expression that you get out of this. But that's an important consideration. Okay. That's an important consideration. And there is one more method, other than the one that we have talked about today. It doesn't work in every case, but in many cases where that method works, it will give you simpler regular expression than the one that you are getting here. Okay, so that method, we will perhaps do in a future class. Okay, Cozen doesn't give that method. Hofcroft book gives that second method also, right? And but currently this is the method. So currently this is all a rather ad hoc. You will be given an automaton. You have no choice on which automaton you are given. You are given some automaton. You are asked to convert it to regular expression. The only choice is which states to remove. What is the sequence in which you will remove the states? So start with state which is connected to more other states. So that lot of paths go via it. That is the only heuristic I can suggest for you. So with that slightly unsatisfactory answer, we'll have to move on. There is not very good theory of relating let us say, the structure of the automaton and the structure of the regular expression you get. Okay. The other thing to note is that this regular expression is very complicated. It can be simplified. So we will be seeing that next. Okay. So there are methods by which regular expressions themselves can be simplified. So you can just write a mechanical algorithm, a Python program which will take this automaton and blindly convert it to, a regular expression, something like this, choosing some arbitrary, heuristic for choosing states to remove. Okay, and you can mechanically get regular expressions like this, which is what you would do for large automata. You would not do this manually. But you have to be able to solve simple examples to understand that construction. Okay. So I think the question was that this regular expression is far too complicated compared to the automaton, right? It's very difficult to see what is going on here, right? You agree?
Yes, sir.
Yeah. So what we want is some sort of way of simplifying this expression. Just as we have got complicated, polynomial, and we want to factorize it, nicely. We want some rules by which you can actually simplify this expression. And that takes us to the next thing, something called the Kleene algebra. That is algebraic laws for equivalence of regular expressions. So we will define, we already defined this. We say that regular expression alpha is equivalent to regular expression beta if and only if the language of alpha is equal to the language of beta, right? And a stupid example is language of, say, alphabet zero plus 1 is same as language of 1 plus 0, right? Because it's union, and union is commutative, right? So two different expressions will give the same language. There will be more complicated examples. Let me take a more complicated example. Language of A star is equal to language of epsilon plus A followed by A star. Do you agree? These two regular expressions, this A star, I will underline them, and epsilon plus A followed by A star have the same language. Intuitively, can you see that? This says either empty string or one repetition of A followed by 0 or more repetitions of A. And this says 0 or more repetitions of A. 0 or more repetitions of A, when you have got 0 repetition of A, you will get epsilon. If you got 1 or more repetitions of A, you will get A followed by 0 or more repetitions. So these two regular expressions denote the same language, right? So we have this notion of equivalence of two regular expressions, right? And we have some rules, just as you got rules which allow us to factor polynomials in arithmetic. We have some rules which allow us to prove equivalence of two regular expressions. And this slide just gives the summary of those rules. But we are going to do these rules a little bit in detail. Okay, so don't worry if you don't understand this summary. But what is the aim? Aim is to take two different regular expressions and show that they are equivalent using some algebraic laws rather than calculating their languages and showing that they are equal, which can become complicated. Okay, so let me jump ahead and give you one example. So here is one regular expression in left. And you have got some sort of distributivity, just as you have got A plus B plus C, multiplied by, in arithmetic, D plus E plus F will give you what? Okay, let me not do it that way. Okay, but here is an example. If you start with the red expression and you kind of get this red expression out of it, and we'll see the laws which will let you do this. Okay, so you can transform this expression to an equivalent expression which looks like this, which is a little bit simpler. So don't worry, we'll see this more in detail, but there are simple rules like this. So first thing that it says is plus is commutative. That is alpha plus beta is equivalent to beta plus alpha. That's obvious. That is plus is commutative. Agreed? What is language of alpha plus beta? Language of alpha union language of beta, which is same as language of beta union language of alpha. So plus is commutative. It is also associative. This is just like arithmetic plus. Union behaves very similarly to this thing, right? Besides, you've got alpha plus empty set. You know, phi denotes empty set. Is same as alpha, right? So I hope these three rules are clear to you about plus. Okay, I think this is called A dot 3. They are numbered in cosine. This is called A dot 4. This is called A dot 5. Okay, so the rules A dot 3 to this is 5 and this is 6. Root A dot 3 to A dot 5 are clear to you. They are very, very easy to prove from the semantics of the plus operator. When you have these three kind of rules, no, what you say is that what you have is a kind of monoid with an identity called phi, right? Because applying that operator with phi gives you alpha. Don't worry about the names, but basically these three rules hold. Also, alpha plus alpha is equal to alpha. Why? Language of alpha plus alpha is language of alpha union language of alpha, but both these alphas are same. So that union will give you the same thing. So what you have, these four rules in mathematician will say what you have is an idempotent commutative monoid. Okay, big names that mathematicians use. Basically, these four rules hold for regular expressions. And they are kind of obvious rules, right? So I hope you have no difficulty with these rules. They're just like rules in arithmetic, where the empty set is like 0 in case of addition. Also, in case of catenation, catenation is associative. Alpha catenated with catenation of beta and gamma is same as alpha catenated with beta catenated with gamma, right? And if you take epsilon catenated with alpha, it will give you alpha. Because empty string catenated with anything will give you the same string back, and when you apply it to every string in alpha, you will get this back. So again, these two rules are simple. And again, this says that we have a kind of monoid under catenation. So I think these are simple rules. You can check that these rules hold from the meaning of the operators that we have defined. So these algebraic rules are true for regular expressions. Okay. You also have that you've got alpha catenated with beta plus gamma. That is same as alpha catenated with beta plus alpha catenated with gamma. So, catenation distributes over union, and it distributes in the forward direction as well as backward direction. So this also holds and this also holds, right? And if you've got empty set, you catenate empty set with anything, you will get empty set. So I think these are all the rules that you need to learn. These are the basic rules of equivalence of regular expressions. And there is one more thing that I need to do. Page after, if every regular expression is equivalent to itself, that is stupid, no? Every arithmetic expression, is equal to itself, right? Also, if you've got alpha equivalent to beta, that implies that beta is equivalent to alpha. This is an it's reflexive, commutative, and transitive relation. This equivalence is a reflexive, commutative, and transition relation. Third property is if alpha is equivalent to beta and beta is equivalent to gamma, then alpha is equivalent to gamma, right? So these simple rules which we take for granted in arithmetic also hold for regular expressions. Okay, so this is what is called reflexive, commutative, and this is transitive, right? And finally, if you've got a complicated pattern gamma, where alpha occurs somewhere inside it, right? So I denote by gamma bracket alpha is gamma is some complicated expression where alpha is a sub expression which occurs maybe several times within gamma. What you can do is you are given such a thing. Now, if alpha is equivalent to beta, then that implies that gamma with alpha occurring in it is equivalent to gamma with, you take that occurrence of alpha in it and substitute it by beta. That is, any sub-expression can be substituted by an equivalent sub-expression. We use these rules very intuitively for arithmetic, and the same thing holds here. So in mathematicians' language, so you can substitute sub-expressions by equivalent sub-expressions to get equivalent things. And that in mathematicians' turn, that shows that this equivalence relation is actually a congruence. That is what an algebraist would say. That is, when you can substitute equivalent sub-expressions to get equivalent expressions, the notion of equivalence you got is a congruence. This is very useful because you can do, equivalent substitutions in subterms and you can get equivalent things. So all these familiar properties hold. And oh my God, I have completely lost the plot. Yeah. Okay. And these simple rules hold, right? Let us see some application of these rules. So I'm going to do this example. So you start with the left-hand side expression, right? Now what happens? Take this. See, trouble with algebra is you should make clear where you are operating. So you are operating on this term. And all of this one can actually be written as epsilon dot 1, right? Plus 0.1 plus 0.0.1, right? This is the underlying sub expression. Everything ends with a 1. So you can factor that out, and what you will get is this will be equivalent to epsilon plus 0 plus 0 0 whole thing dot 1, right? So this one you can pull out, and that is what he has done here. He has substituted by this. Rest everything remains as it is. He has not changed anything. Okay, so this red underlined term, he has written this by factoring this end one out of all the 3 terms, right? He has basically applied this step to rewrite this as this. And that, why is that allowed? Because you've got a rule which says, this rule which says if you've got alpha plus beta, whole thing catenated with gamma, that is same as alpha gamma plus beta gamma. So given such a thing, you can factor out that gamma and do it. So he's done that substitution and got this, right? That is the first thing. Next thing, what does he do? He actually factorizes this red part into these 2 parts. Why? Using distributivity. So you take the lower red part, and by distributivity, this will be same as epsilon dot epsilon plus 0 dot epsilon plus epsilon dot 0 plus 0 dot 0 and 0 dot epsilon dot epsilon. So this red thing will be equivalent to this. Epsilon dot epsilon will give you epsilon plus 0 dot epsilon will give you 0 plus 0 epsilon dot 0 will give you 0 and plus you will get 0 dot 0, right? Now by idempotency, 0 plus 0 will give you same as 0. So you will get epsilon plus 0 plus 0 dot 0, which is what you had here in the upper thing. So the upper red thing can be written as this 2 factors. Similarly, this blue thing can also be factorized as this. So basically, using all these equivalences, the left-hand side expression can be factorized to the right-hand side expression. So you see the use of these laws in simplifying regular expressions. You can simplify an expression like this into something which looks like this. Okay, that is it. And so far we have dealt with rules which deal with plus and catenation, right? And of course, the basic operators phi and epsilon, etc. The star operator we have not considered. And the rules for star are a little bit complicated. So I will not be asking you many examples about this, but you know, these are the basic rules for the star operator. Now here, of course, I'm using a less than equal to symbol. So I say that regular expression alpha is less than regular expression beta if language of alpha is a subset of language of beta. Okay, so this less than means language containment. And then there are these 4 rules. Okay, so using those 4 rules, these identities can be derived. The derivations are a little bit messy, but each of these identities by itself is easy to understand. You can convince yourself that this identity is whole, right? For example, epsilon plus alpha star says what? Either you can have epsilon or you can have alpha, and this you can repeat 0 or more times, which is same as epsilon alpha star. Can you guess why these two are true? Why this rule is true? Because anything that matches right hand side will look like alpha, 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 alpha some number of times, right? You can get that by just choosing alpha so many times and get this. If you had something on the left hand side, what would you get? Suppose there was something that matched the left hand side, which means what? Epsilon plus alpha is repeated some number of times. But epsilon plus alpha is union of epsilon. So you would have maybe chosen an alpha here and then, an epsilon, then an alpha, then maybe another alpha, then an epsilon, and then an alpha. So you'll have some sequence of choice of either alpha or epsilon. That is what the left hand side, this term is saying. Epsilon plus alpha star will look like this. And all these epsilons don't contribute anything. Anything dot epsilon will give you that thing only. Epsilon dot alpha is same as alpha. So you can remove all the epsilons here. You will get some number of repetitions of alpha. So it will be included in alpha star. So I think I've given you a kind of intuitive understanding of why this rule holds. You can check for yourself that all these rules hold. Forget about these rules. First two are easy. Forget about these 2 rules. Okay, they are important, but we are not going to use them. Okay, we are just going to use these rules, right? And these have been given numbers. I think this is called Cosen's number for this is A.17. So this will be A.16, I think, or something like this. Okay, so all these identities are there. Now your job is to convince yourself that these identities hold. But once you have these identities, remember this complicated expression that we got, this one, okay, it can be simplified. And here is a simplification of that expression from Cosen. I've written whatever we got here in the first line. And then by applying those identities that we gave, we can simplify it to this expression. So I think I will not do this proof in this class. We will defer this to, but proofs are very, I mean, they are very boring to do. I think you have to understand them yourself. So I would urge you to look at this proof of equivalence of regular expressions using the laws that we have done and check that you are able to understand this proof, right? So the method is that given an NFA, we convert it to an equivalent regular expression, arbitrarily removing states one by one from the automaton, and you will get a complicated expression. Then you simplify it using the algebraic laws, and then you get a simple expression for the regular expression for the language of the automaton. That is the method. Okay. And that finishes the topic of regular expressions. So let me say the following. You will be asked to prove equivalence of things, but it will not make use of these 2 laws. The ones given, which I have crossed out. Let me cross them out in blue. These laws you will not be required to do, but the remaining laws you will have to apply in order to simplify the expression. So you should get some familiarity with simplifying expressions using these laws. You don't have to use these 2 laws. Okay, we will just use the remaining laws. Any questions?
Sure.
Yes.
Regarding the congruence property,
Yes.
like you said that if gamma is some regular expression containing alpha as sub-expression,
Yes.
then you can replace alpha by beta.
Right.
So, is it true that if for some expression gamma which contains alpha as a sub-expression,
Yes.
if we replace alpha by beta and we get the same expression, then does that imply that alpha is equivalent to beta? Like, is the converse also true here?
No, no, no. The converse need not be true. The converse need not be true. So, it depends on what kind of gamma you use, right? For some gammas, for example, I will give you an example, right? Let me give you an example. That's a good question. Who's asking this question?
Ishan.
Ishan, take this, take the regular expression phi dot alpha. This will always be equal to phi dot beta for any alpha and beta. Because empty set catenated with anything will give you empty set. This will in fact be equal to phi, right?
Yes,
this will hold for any alpha beta. This does not imply that alpha is equivalent to beta, right?
Yes, sir.
So but that's a great question because there are specific gammas for which that property holds. Okay, there are some sort of unifiers of alpha and beta. And it's well known that what sort of gammas will prove that, and that is the method for using those kind of gammas. Sometimes alpha equivalent to beta is also proved, but that's a little more sophisticated method that you are talking about. In general, it does not hold. Okay.
So
I'll give you an example, counter example.
The
right?
example is just when gamma of alpha is equal to alpha, right? Because then you'll directly get alpha equivalent to beta.
Right, right. But in general, the converse does not hold. I hope that answers your question. I can point you to, what you are talking about, are basically fundamental properties in algebra, okay? In universal algebra, in fact. And they have discussed such questions at length, okay?
Yes, thank you.
Yeah, but that's an interesting topic actually. For what kind of gammas, by knowing that can we have reverse implication, and for what gammas, that is the kind of question that universal algebra has addressed. Okay. Yeah. So I think if there are no more questions, I know today we have done a lot. I urge you to study this. I will be releasing a homework for you today, and that homework will be useful for you for the exam. And in the next class, we are going to take a tutorial on some of those exercises. Okay, so please study today's slide and do the homework. Is that okay? That homework will very much help you in the midterm. All right. So I think if there is nothing more, I will close the recording.